Imagine this, $125 million gone in an instant. That's what happened to NASA's Mars orbiter in 1999. It was a huge loss for NASA and for space exploration. The reason? A simple mistake, a mix-up in units of measurement. It seems unbelievable, but it happened. This disaster highlights just how important communication and attention to detail are in space exploration. We're talking about missions costing millions, even billions of dollars. The stakes are incredibly high. The Mars Climate Orbiter was on a mission to study Mars's climate and atmosphere. It was supposed to orbit Mars, taking pictures and collecting data. This data was critical for understanding the Martian climate, its history, and the potential for life. The mission was a big deal for NASA. It was a key part of their Mars exploration program, which aimed to learn as much as possible about our red neighbor. The loss of the orbiter was a huge setback. It delayed future missions and forced NASA to rethink its approach to communication and data management. The Mars Climate Orbiter was more than just a spacecraft. It was a sophisticated scientific laboratory designed to unlock the mysteries of the Martian climate. Its primary goal was to collect data on Mars's atmosphere, helping scientists understand its composition, temperature variations, and the forces that drive its weather patterns. This data was crucial for piecing together the history of Mars's climate, from its warmer and wetter past to its current cold and arid state. By studying the Martian atmosphere, scientists hoped to gain insights into the planet's past habitability and the potential for life to have existed there. The orbiter was equipped with a suite of instruments capable of measuring various atmospheric properties, including temperature, pressure, humidity, and the presence of dust and water vapor. These measurements would provide a detailed picture of Martian weather patterns and how they change over time. One of the key objectives of the Mars Climate Orbiter was to create the first comprehensive maps of the Martian atmosphere. These maps would show the distribution of different gases, the temperature variations across the planet, and the patterns of wind circulation. By studying these maps, scientists hope to gain a better understanding of the Martian climate system, including the factors that influence its weather patterns and how they differ from those on Earth. The orbiter was designed to orbit Mars for at least one Martian year, which is equivalent to about 2 Earth years. This extended mission duration would allow scientists to observe seasonal variations in the Martian atmosphere and create a more complete picture of its climate dynamics. Another critical aspect of the Mars Climate Orbiter's mission was to search for evidence of water on Mars. While previous missions had provided promising hints of past water activity on the planet's surface, the orbiter's instruments were designed to look for signs of water in the Martian atmosphere. By measuring the concentration of water vapor in the atmosphere, scientists hoped to determine how much water is present on Mars today and where it might be located. This information would be crucial for understanding the history of water on Mars and its potential role in shaping the planet's climate and geology. Additionally, the presence of water is considered a key ingredient for life, making its discovery on Mars a significant milestone in the search for extraterrestrial life. The Mars Climate Orbiter was not only a scientific endeavor but also a technological stepping stone for future Mars missions. It was designed to serve as a communications relay for subsequent missions, including the Mars Polar Lander, which was scheduled to land on Mars just a few months later. The orbiter's ability to relay data back to Earth from the Martian surface would have greatly enhanced the scientific return of these missions. Additionally, the lessons learned from the development and operation of the Mars Climate Orbiter would inform the design of future spacecraft and mission architectures. The orbiter's mission, though ultimately unsuccessful, was a testament to NASA's commitment to exploring Mars and unraveling its secrets. It paved the way for future missions that would build upon its legacy and continue the quest to understand our enigmatic planetary neighbor. The Mars Climate Orbiter disaster wasn't caused by a malfunctioning instrument or a sudden technical glitch. It was a much simpler, almost unbelievable error, a mix-up in units of measurement. One team at NASA, the team responsible for the spacecraft's navigation, was using the Imperial system, which uses pounds and inches. Another team, the team responsible for the ground-based software, was using the metric system, which uses newtons and meters. This might seem like a small detail, but in the world of space exploration, even tiny discrepancies can have catastrophic consequences. And in this case, it did. The imperial and metric systems are fundamentally different ways of measuring the world around us. The imperial system, with its origins in ancient Roman and British units, is based on arbitrary standards. The metric system, on the other hand, is a decimal system, making it much easier to use and convert between units. In the context of the Mars Climate Orbiter, the discrepancy between these two systems meant that the spacecraft was receiving instructions that were off by a factor of 4.45. In other words, for every 1 newton of force that the ground-based software thought it was commanding, the spacecraft was actually receiving 4.45 pounds of force. This seemingly small difference had a cumulative effect, gradually pushing the orbiter off course. How could such a fundamental error occur in a project as complex and meticulously planned as a Mars mission? The answer lies in a combination of factors, including communication breakdowns, overconfidence, and a lack of rigorous oversight. The teams working on the Mars Climate Orbiter were geographically dispersed, with one team located at NASA's Jet Propulsion Laboratory in California and the other at Lockheed Martin in Colorado. While both teams were highly skilled and experienced, the critical information about the different measurement systems being used was not effectively communicated or documented. As the mission progressed, there were warning signs that something was amiss. Data from the orbiter indicated that it was drifting off course, but these warning signs were either dismissed or misinterpreted. The teams involved were under immense pressure to keep the mission on schedule and within budget, which likely contributed to a culture where potential problems were downplayed or ignored. The assumption was that everyone was working with the same understanding of the units being used, an assumption that proved to be fatally flawed. The Mars Climate Orbiter disaster serves as a stark reminder of the importance of clear communication, meticulous attention to detail, and a culture of safety in space exploration. It highlights the need for standardized procedures and rigorous checks and balances to prevent even the smallest errors from cascading into catastrophic failures. The financial cost of the disaster, $125 million, was significant. However, the loss of scientific data and the setback to Mars exploration were perhaps even greater losses. The disaster forced NASA to reevaluate its processes and implement new measures to prevent similar mistakes in the future. It served as a painful but valuable lesson in the unforgiving realm of space exploration, where even the smallest oversights can have devastating consequences. The Mars Climate Orbiter embarked on its journey on December 11, 1998, launched atop a Delta II rocket from Cape Canaveral Air Force Station in Florida. The launch was flawless, a testament to the engineering prowess of NASA and its contractors. The spacecraft soared through the atmosphere, leaving Earth behind as it set course for its destination, the Red Planet. The early stages of the mission, known as the cruise phase, were relatively uneventful. The spacecraft traveled along its planned trajectory, its systems functioning nominally as it hurtled silently through the vast emptiness of space. Engineers and scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, meticulously monitored the spacecraft's progress, their excitement building with each passing day as Mars drew closer. The Mars Climate Orbiter, despite its relatively small size compared to other interplanetary spacecraft, was a marvel of engineering. Weighing in at just over 600 kilograms, it was packed with a suite of scientific instruments designed to study the Martian atmosphere and climate. Its primary instruments included the Pressure-Modulated Infrared Radiometer, or PMR, designed to measure the temperature and humidity of the Martian atmosphere, and the Mars Color Imager, or MARCI, a camera capable of capturing high-resolution images of the Martian surface and atmosphere. The spacecraft was also equipped with a radio science experiment that would use the spacecraft's radio signals to study the Martian gravity field and the structure of its atmosphere. To power its instruments and communicate with Earth, the orbiter relied on 2 solar arrays that converted sunlight into electricity. Behind the sophisticated technology of the Mars Climate Orbiter was a dedicated team of engineers, scientists, and technicians who had poured years of their lives into making the mission a reality. They were the unsung heroes of the mission, working tirelessly behind the scenes to ensure its success. At NASA's Jet Propulsion Laboratory, the mission control team worked around the clock, monitoring the spacecraft's health, planning maneuvers, and analyzing data. The science team, spread across various universities and research institutions, eagerly awaited the data that the orbiter would collect, hoping to unlock the secrets of the Martian climate. And at Lockheed Martin, the company that built the spacecraft, engineers stood ready to troubleshoot any problems that might arise. It requires incredibly precise calculations, taking into account the gravitational pull of multiple celestial bodies and the spacecraft's own motion. The navigation team for the Mars Climate Orbiter relied on a complex network of ground-based antennas and sophisticated software to track the spacecraft's position and velocity. They used a technique called radiometric tracking, which involved sending radio signals to the spacecraft and measuring the time it took for the signals to return. By analyzing the Doppler shift of the returning signals, they could determine the spacecraft's speed and direction. These measurements, combined with sophisticated mathematical models, allowed the navigation team to determine the spacecraft's trajectory and make any necessary course corrections. As the Mars Climate Orbiter drew closer to its destination, the navigation team began a series of course correction maneuvers designed to fine-tune its trajectory and ensure that it would enter Mars's orbit at the correct altitude and inclination. These maneuvers involved firing the spacecraft's thrusters for precise periods to adjust its speed and direction. However, as the mission progressed, the navigation team began to notice discrepancies between the spacecraft's actual trajectory and its predicted trajectory. The discrepancies were small at first, but they grew larger over time, raising concerns among the team. They attributed these discrepancies to errors in their measurements or uncertainties in their models, but they could not pinpoint the exact cause. On September 23, 1999, after a journey of nearly 10 months, the Mars Climate Orbiter was scheduled to perform its final maneuver, a Mars orbit insertion burn that would slow it down and allow it to be captured by the planet's gravity. The maneuver was critical. If successful, the orbiter would enter an elliptical orbit around Mars, ready to begin its science mission. However, as the spacecraft disappeared behind Mars, its radio signal, which had been strong and steady just moments before, vanished abruptly. The mission control team at JPL waited anxiously for the signal to return, hoping that it was just a temporary outage. But as the minutes stretched into hours, the realization dawned that something had gone terribly wrong. The Mars Climate Orbiter, it seemed, was lost, and with it, years of work and the hopes of unlocking the secrets of the Martian climate. The Mars Climate Orbiter mission control room, usually abuzz with activity and the chatter of scientists and engineers, fell eerily silent. The large screens that normally displayed telemetry data from the spacecraft, showing its vital signs and its progress toward Mars, were blank, their emptiness amplifying the growing sense of dread in the room. The team had gathered, as they had countless times before, to witness the culmination of months of meticulous planning and hard work, the moment when the Mars Climate Orbiter would fire its engines and slip into orbit around the red planet. But instead of the anticipated signal confirming the maneuver's success, there was only silence, a deafening silence that spoke volumes about the fate of the mission. The minutes that followed were the longest of their lives, each tick of the clock a hammer blow to their hopes. The atmosphere in the room was thick with tension, a palpable mixture of disbelief, confusion, and a growing sense of despair. As the initial shock began to wear off, a frantic search for answers began. Engineers huddled around computer terminals, their faces illuminated by the cold glow of the monitors, desperately reviewing telemetry data from the spacecraft's final moments. Scientists, their faces etched with concern, tried to make sense of the situation, their minds racing to come up with possible explanations for the spacecraft's sudden silence. The team, accustomed to solving complex technical challenges, struggled to comprehend how a mission that had gone so smoothly for so long could unravel so catastrophically in its final moments. The search for answers quickly expanded beyond the confines of the mission control room, drawing in experts from across NASA and its contractor network. Every line of code, every calculation, every system on the spacecraft was scrutinized, hoping to find a clue, any clue, that could explain what had gone wrong. In the hours and days that followed, a glimmer of hope emerged. Initial analysis of the limited telemetry data received before the signal loss suggested that the spacecraft might not have been destroyed, but might have survived its encounter with Mars, albeit in an unexpected and potentially uncontrollable orbit. Perhaps, some dared to hope, the Mars Climate Orbiter was still out there, circling the red planet, waiting for a chance to re-establish contact. Teams worked around the clock, adjusting ground-based antennas, fine-tuning their tracking software, and sending out a continuous stream of commands, hoping for a response, a sign that the spacecraft was still alive. But as days turned into weeks, and the silence from Mars remained unbroken, the harsh reality of the situation began to sink in. The glimmer of hope that had sustained them began to fade, replaced by the crushing weight of failure. The loss of the Mars Climate Orbiter was more than just a technical failure. It was a deeply personal loss for the men and women who had dedicated years of their lives to the mission. The sense of disappointment was profound. They had poured their hearts and souls into the project, only to see their dreams dashed against the unforgiving reality of space exploration. The failure was a bitter pill to swallow, a stark reminder of the unforgiving nature of their work, where even the smallest mistake could have catastrophic consequences. But amidst the disappointment and heartbreak, there was also a sense of resilience. The Mars Climate Orbiter may have been lost, but the spirit of exploration remained undimmed. The loss of the Mars Climate Orbiter was a stark reminder that even in the highly advanced world of space exploration, seemingly small details can have catastrophic consequences. The $125 million disaster, a result of a simple unit conversion error, served as a wake-up call for NASA and the entire space exploration community. It underscored the critical importance of clear communication, rigorous testing, and meticulous attention to detail in every aspect of a mission, from design and development to launch and operations. The failure prompted NASA to reevaluate its processes and implement new procedures to prevent similar mistakes in the future. One of the most significant outcomes of the disaster was the agency's renewed emphasis on standardized procedures and cross-team communication. Recognizing that the root cause of the failure lay in a breakdown of communication between different teams, NASA implemented new protocols to ensure that all teams involved in a mission are using the same units of measurement, software systems, and testing procedures. The Mars Climate Orbiter disaster, though a significant setback, strengthened NASA's resolve to explore Mars and the cosmos. It highlighted the importance of learning from failures and using setbacks to innovate. NASA emerged with a renewed sense of purpose and a deeper understanding of space exploration. The lessons extended beyond the mission's technical details. They reminded us that space exploration requires safety, transparency, and continuous improvement. The legacy lives on in missions that followed, expanding our understanding of the universe. Each mission, a testament to human ingenuity, carries lessons from past failures, ensuring we continue to reach for the stars.